Welcome to the fifth unit of the second week in the Parallel Programming Concepts course. My name is Peter Tröger. We discussed different aspects of concurrency and saw that concurrency programming or concurrent programming actually means that we try to formulate independent activities, and at some points in time we have to synchronize their work in order to avoid race conditions. We do this with synchronization primitives, for example with semaphores and mutexes, or with the concept of a monitor. When you look into modern programming languages and modern programming environments, you will quickly figure out that semaphores and mutexes are treated as the lowest level of synchronization and concurrency management you can find. In typical frameworks today, you find a lot more elaborated or advanced concurrency mechanisms. In this unit, we want to shortly go through them and have a look on how they work and what they mean. If you're interested in the very specific details of these constructs, I would recommend to consult the documentation of your favorite programming language and play around with the concepts. The overall idea is always similar, so we mainly want to focus on the terminology and the kind of concepts here in this part of the course. The first thing we can discuss is a little bit of a surprise for some people, and this is the spin lock. Spin lock is a synchronization primitive that allows you to use a waiting loop on a status variable. So this is something that intentionally performs busy waiting. So you have a loop spinning on a variable and checking if the condition is changing, and this is purely implemented by, as the name says, spinning over the synchronization variable and trying to figure out when the condition is fulfilled that we are waiting for. The surprise here is that the original argumentation from the semaphore discussion and the mutex discussion was always that doing a busy wait in a wait call is a bad thing because we're eating up CPU resources and cycles for no good reason, and the operating system better put such activities to sleep. The reason for having spin locks as an explicit concept lies in the fact that we may have situations where the overhead of using a full-fledged synchronization primitive is too high. The typical example is inside operating systems, for example in driver programming, when you really want to save time being used for actually doing the synchronization. The second condition is that you may already know from your code that the waiting time will be extremely short. So if you have an extremely short waiting time, and this is for sure, then the whole overhead of putting your thread to sleep and the operating system scheduler and dealing with the memory management when this happens and then waking it up again when the condition is fulfilled, this kind of overhead really eats up most of the performance. So if you want to have a smaller and faster solution, it may be good enough to have a few cycles of spinning on the variable because you anyway know that this thing will end soon. One of the important aspects of spin locks is that they only make sense in usage if you have multiple processing elements, so a multi-core or multi-processor machine. If you do spin lock operations on a uniprocessor machine with only one processing element, there is no chance that a second activity is actually releasing your condition or releasing your lock while you're spinning on the lock variable because you have only one processing element and only one activity at a time. Therefore, if you use spin locks as a high-level concurrency concept, please make sure that you only use this when you know that the target platforms are multi-processor platforms. The second high-level primitive that can be commonly found in literature is the so-called reader-writer lock. A reader-writer lock is a special case of a mutex, so it also protects a critical section from concurrent access or from parallel access by different concurrent activities. A reader-writer lock allows you to have multiple so-called reader activities, reader tasks inside the critical section at the same time, while another class of activity could be a writer, and this writer should have exclusive access to the critical section. So the idea here is that you have a more high-level scenario for your synchronization that is already implemented in this reader-writer lock synchronization primitive. So somebody else did the work for you and figured out how to do this, for example, based on plain mutexes. in a very efficient and operating system or language runtime optimized way. So if you have this given in your runtime environment or in your operating system, it's a good idea to use it because somebody else solved all the nasty little details for you and made sure that this works in a smooth fashion. Reader-writer log then allows you to declare activities, concurrent activities, either as writer or reader activity, and to deal with the logging accordingly. The implementation of a reader-writer log can be optimized according to different performance characteristics. For example, you could aim for a minimum delay for readers when they're waiting for entrance to the critical section, or you could optimize your whole algorithm on a minimum delay for the writer. So this depends a little bit on your application, and in modern languages and runtime environments, you will find different variations of reader-writer logs where you can choose which is your most preferred behavior of the concurrency synchronization primitive. Another thing that is quite common today in high-level runtime environments or languages are concurrent collections. A collection is a data structure such as a queue or a set or a list or a hash map that allows you to deal with multiple data items at a time. And such collection data types are a classical thing in programming languages, but now we have a lot of implementations for so-called concurrent collections, which means that the language library or the class library or the operating system gives you concurrent collection implementations that are already done. So you have the possibility to read and write from these or to these different collection types concurrently from different threads or processes or tasks without dealing with synchronization issues. So these synchronization issues are already solved for you. You typically have put and get or fetch operations that are defined on this data type, and you can use them and you can be sure that somebody else solved the internal synchronization problem for you. This is again a good thing because it saves some time for you. You can be sure that the whole critical section problem is really solved and you don't run into inconsistencies or race conditions inside the handling of the data. So if you have them, reuse them in order to make your life easier. The next example for high-level primitives is a so-called reentrant log. We already discussed that with the mutex example. So a reentrant log has a special semantic that you can reacquire the log several times without having any kind of counting semaphore variable being increased constantly. This is crucial for implementing several classes of algorithms, such as cyclic algorithms, where you really have the situation due to recursion or any kind of backtracking mechanism that you have logs being acquired several times because the code is run several times. This is especially useful when the bookkeeping for doing the according number of unlocks would add a lot of memory consumption or computational effort to your program. If you have a reentrant log, one unlock is enough, regardless of the fact how many logs you did beforehand. So if you have this situation in your code that you don't know how many times your log operation will run, or if you find it hard to do the bookkeeping, then maybe you want to use such a given high-level concurrency primitive. The next interesting high-level primitive we will later in this course talk about again are barriers. In general, are barriers a concurrency concept where the different concurrent activities meet at a particular point in the instruction stream. The idea here is that you have participants and the barrier somehow acts as an overall synchronization spot. This is not a critical section. It is only intended to make sure that regardless of the local execution speed of the different concurrent activities, they all meet at that point and continue from there again. There are different variations of barriers. A newer concept are dynamic barriers, where the number of concurrent tasks participating in this barrier can be decided at runtime. This is especially needed for example, for fork join models, as we will learn about next week in OpenMP. But it's also needed in shared nothing environments. And another variation of the overall concurrency barrier concept are memory barriers, where you can enforce the separation of memory activities. So you make sure that all concurrent activities, all concurrent code finishes its memory activities, reading and writing from memory, before the barrier, before they all continue. This becomes relevant when you talk about caching optimizations, dealing with the memory wall. There you want to have a possibility to ensure memory instruction ordering at some point in time. So whenever you have a memory access and race condition possibility in your code, you better start to use memory barrier instructions or so-called memory fence instructions. This picture shows you a little symbolization of what happens with a barrier implementation. So we have three activities, three tasks running in different execution speed. They run concurrently, maybe they run in parallel if we have parallel hardware given. And the first task is reaching the point of the barrier at a particular point in time. So in physical time, he's the first. And he is now waiting until the other tasks actually also ended up at the barrier instruction, and from there all of them continue. Barriers are typically implemented by shared variables, so you have a shared barrier variable and all of the tasks call some kind of wait or block function in the execution, and this function only returns if all of the participants made their call to the barrier block function. Another important high-level primitive we need to introduce in general here, we will later use them again in particular programming environment examples, are futures. Futures are a concept that can be typically found in object-oriented languages, and the idea is that you get a proxy for an upcoming result. So you call a method and or some kind of functionality, and this functionality may take an arbitrary amount of time, so it takes a while. And this is problematic because you actually don't want to block on this thing. You may have other things to do in your code. And with futures, you have the idea to do something like an asynchronous function call. So you call the functionality, you get an immediately return from the function, but instead of the real result, you get a placeholder for the result. You get a proxy for the result. And this proxy is called a future. You can now use this future and pass it around, or you can just put it aside and do some other work. And finally, if you are at the point in your execution where you see, okay, I did all the work I could manage to do in between, I now really need that result expressed by the future. Then you can call a blocking function in order to get the final result. You see here a C++ example in this picture. So we have the main function and we have the future definition, and the std async call launches an asynchronous activity based on an anonymous function here in C++. So this is C++ 11. And we get an immediate return from this call, and this return result is expressed by the future variable. When we call the wait function in C++ 11, we get a blocking until the actual result of the asynchronous execution is available. So this is an interesting concept that allows you to write a more asynchronous and flexible behavior in your code. It's a pure concurrency concept, and it's reused in several programming languages and programming paradigms we will learn about in the upcoming weeks. An even more elaborated high-level primitive is the so-called log-free programming. This is not only a primitive, but basically a whole research field and also a class of different approaches. Log-free programming means that you share data in concurrent tasks without actually using any more logs. All the things we talked about until now rely on the fact that you have mutexes or semaphores or reader-writer logs or barriers, some kind of variable that allows you to wait for the condition so that you have a predictable interleaving of concurrent activities, and then to continue. And with log-free programming, we want to have data structures, shared data structures, that need no logging at all. This is an interesting aspect. It basically relies on the clever usage of hardware support for atomic instructions, something like compare and swap. So if you're interested in this topic, we put some additional readings on the page in order to give you the necessary insights. In general, log-free programming is an approach to deal with deadlock and life conditions and to hopefully make them go away. There is still active research in that field, and for all the things that are available, the easiest way to use them is to simply rely on high-level concurrency primitives, such as concurrent collection classes or other things. If we now summarize the overall idea of concurrency we heard about this week and the different problems we may have and the solutions for this, we see that this is not really an overall solution for the concurrency problems, what we have at hand with the tools given, but it's basically some stuff we may rely upon to deal with that problem ultimately in our program itself. So the message here is, if you want to deal with concurrency issues, and concurrency issues are the ones you will face in your parallel program, then you need to understand the problem. You need to have some good approach of identifying potential race conditions, and you need a good way of solving them. The easiest solution is always to design your program in a way that you have no critical sections at all. So this is what Brashears in his 8 simple rules for concurrency calls identify truly independent computations. Whenever you have the fact that you can define concurrency or parallelism in your application with no interrelationship, no shared state, no shared variables, then you basically have no more critical sections at all, so you don't have to deal with that problems at all. That is a fantastic thing, and there are systems out there, for example, like MapReduce frameworks, where this is one of the design patterns that you define independent computations. It doesn't work all the time, or you may have infrastructure that solves the critical section problems for you. From a programming point of view, we will see in the upcoming weeks which languages try to help you with the definition of independent computations, for example, by restricting the space of options you have in formulating an algorithm. Another rule from Brashears is that you should implement concurrency on the highest level possible. So if you do fine-grained concurrency or fine-grained parallelism, a lot of interleavings may happen, a lot of activities are running, and so this is very hard to control and to reason about when you look on your code. So it's better to try to realize coarse-grained concurrency. This also relates to the fact that the serial execution speed today in processing elements is very fast. So it is okay to have large blocks of serial code and then a few of them being run concurrently, maybe on parallel hardware. Plan early for scalability, which again relates to the interdependency question, and try to reuse other people's implementations. So one of the main messages from this course is a lot of the things that you're dealing with in parallel programming and concurrent programming are already solved in one or the other way, in particular programming languages, in terms of high-level primitives. So if you have these high-level primitives, if you have concurrent collections or other kind of prepared data structures, please use them, because then you have not the burden of identifying race conditions by yourself. Never assume a particular order of execution. That should be clear meanwhile, that due to the fact that we don't know how our concurrent software runs on either parallel or non-parallel hardware, we cannot make any assumption on the interleaving of instruction or the execution time behavior. And the last rule by Brashears, and this is more from a practice point of view, is don't change your algorithm for better concurrency. So it may be tempting to squeeze out additional performance from your algorithmic implementations by bringing in a lot of concurrency, defining tasks, and doing a mapping on parallel entities. The question is always, do you have a good understanding of the algorithm so that you don't sacrifice correctness for performance? So if you introduce concurrency and you're no longer sure if this actually changes the correctness of your algorithm, then your concurrency might not be worth it. And with this statement, we are finalizing the second week of the parallel programming course. We talked about parallelism and concurrency as general concepts. So we have parallel programming, but parallel programming is actually concurrent programming with the additional consideration of the speed-up question. So we want to make sure that our concurrent activities are well prepared to run in parallel on a piece of parallel hardware. Even with this in mind, we still have to deal with the concurrency issues that are well known for decades in the programming language and the community and in the code development environment. So concurrency problems that we have to deal with are typically boil down to race conditions, where our concurrent activities have an unpredictable interleaving of their atomic instructions, so we don't know how they will behave at the end in terms of timing on the parallel or hardware or the non-parallel hardware. And this leads to the fact that if your program is not designed in the right way, if it has race conditions, then you may run into deadlock or livelock or starvation problems with your code. And in order to protect you from this, or in order to solve that problem, what you need to do is you need to bring some kind of predictable ordering into the parts of your code where this ordering is crucial, where it is relevant. And this is something you do with the concept of a critical section. So a critical section is a part of your code where different concurrent activities somehow meet because they're accessing a shared resource, and you want to make sure that either only one of them is accessing this resource or that there's a particular ordering. And in order to implement this, you have different primitives available, mainly from operating system point of view or in higher software layers as abstractions of these concepts, something like counting and binary semaphores or mutexes. We also talked about the monitor concept as one example of a high-level primitive for concurrency, but we also discussed in this unit stuff like reader-writer logs, barriers, and futures. And with this understanding now of theoretical concepts and the overall idea of concurrency, we will move on to the third week afterwards. And in the third week, we will now target the question, given these abstract concepts and the abstract notion of concurrency, how does that look like in real programming languages? So we will talk about things such as C++11, Java concurrency, and OpenMP. And hopefully I see you again in week number 3. Thanks.